This was AM. Is it FM?
No, it's AM.
This is FM. Because I think it's actually going silent. Because in FM now you're tuning to 150, which is exactly the frequency there. So you just hear the variation of the clock. So anyway, just a quick demonstration to make it reasonably likable that there's information there that you might want to get out. So now we switch the setup. And I'll quickly explain what this is doing, because we need to boot up the test program again here. Oops. Let me just put this here. So I'm now putting the probe, as it is shown there, directly above the CPU, while it's attached to a battery to reduce noise, and then again to the oscilloscope. What we also have is an external trigger, because when you're running something and it's running pretty fast, if you just hook on your oscilloscope and wait till it comes by, you won't see it. So you do want to do a very accurate triggering to find your program. So what I do now is switch to our tool. So this is a tool that we use in our company and also sell to do this kind of analysis. And it's kind of handy because it combines acquisition and analysis. So we can show just the acquisition part now. And what it will do is just, I think it just does 5 DES operations. It's still relatively visible. Maybe put it a bit better. See if the signal becomes. So, if you're a little bit familiar with DES, do you recognize something in this? Yes, the 16 rounds of the DES are clearly visible. So, well, again, that's another bit of proof that this is very likely to be usable in some form or other. So, good thing, yeah. So what can we do with it? What can we do with traces, measurements that we've taken? A trace is a word for a measurement for us. The first thing that you can do is start reverse engineering the information. If you see something like this and you see the rounds, it tells you something. But also, if you would do the same thing for the boot process, for instance, you could also maybe see what's happening in the boot process. Maybe you can identify where it's going over the memory. Maybe you can identify where it's making a signature. Maybe a decision on a signature, stuff like that. You can also zoom in and maybe find very detailed differences. In this case, the bottom trace shows you 2 traces that are almost similar. And what you'll see is that, well, the first part is practically similar, and then suddenly something happens there, and then it becomes actually similar again, but now shifted in time. So apparently there was some decision here where the first time it took longer, and the second time it was shorter. And actually what this was is a lookup table in a crypto algorithm where the table is 512 bytes. And this is an 8-bit processor. So what it's doing is it needs to look up this index, but it's only got 8 bits. So half of that single bit, that 9th bit, has been made into a decision, whether to go for the left table or the right table or the up or the lower, whatever. And that manifests itself as a time difference that you can see when you measure. And if you know that this is related to a key, you can just do a couple of measurements with certain input data and figure out what the key is. Okay, another form is differential analysis. So it's not always so easy that you get measurements that are so different that you can see the information visually in it. In this case, the traces are pretty equal. You don't really see a difference. Only when you take the difference, you start seeing information. In this case, apparently, at the third peak, something happened that's related to, in this case, the input. Because between the two traces, input was varied, and apparently this is related to that input. It might, of course, also be noise, but then the trick is to just take more measurements with more random inputs to see which part of the information is actually related to the difference that you're measuring. And that's what's called differential power or EM analysis. Now, I'm not going to go into all the mathematical details of how you do a correlation, but you have to think statistics and the fact that you want to have a population with a lot of random inputs, for instance, where you can make at some point a distinction, reduce the noise and find the information in the input that's relevant for some part somewhere in the output or in the measurement. And if you make such a correlation, you get something like this, where every time there's a high value, it means that for that bit of information, there apparently was a correlation in the measurement. Now, these are bits from the input data. So we've put data into an algorithm, and every time a little bit different data, just random, and it can be a lot of data. So you can do like 1,000 measurements, 100,000 measurements, 1,000,000 measurements. Just sufficient to reduce the noise and make the correlation visible. And it doesn't have to be visible to the eye as long as your program can distinguish between the noise and the correlation. But these are very nice pictures. They are very clear, and it helps us to see what happened in this algorithm. And in this case, it's again a DES operation. And what you can see is that the input bits of the data for a DES are operated at different moments in the algorithm, which is correct if we look at a DES, but we'll get to that a bit later. Suffice to say that you can see that the bits are split into the left and the right half. So even and uneven are moving to two different times in the algorithm. And you can imagine that if you can do this with the key information, that you could also find the key. The only thing is you have no way to randomize the key. There's no point in being able to randomize the key. So you can't use this directly to find a key. For the input, you can use it directly. You can directly correlate your input with the measurements and find where it's used in the program. For the key, you have to figure out something else. And that's the differential power attack that I'll show after this. Just a short break back to secure CPUs. So what we're seeing is that instead of a CPU being dependent on external storage and crypto and software, CPUs are changing in that they are actually storing secret keys inside themselves. They are blown in there by fuses or programmed into OTP, and they have their own crypto engines to operate on them. So the secret key never has to leave the CPU, and it can be used to secure all the other parts of the chip. It can be used to securely enable or disable the debug interfaces. It can be used to authenticate to flash chips, for instance. So to attack such a system, the DES key, for instance, or the AES key in there becomes a very valuable property. So that's the thing that you would want to attack with a side channel attack. Notice that I also shown an external communication channel there. The question, of course, is always, what's the easiest attack? Is it easier to do a side channel than, for instance, try to break just the client application on the CPU. I think now in the parallel session, there's a discussion on the iPhone that has been broken by a bug in the Safari browser. So they have all this code signing and maybe other security features, but they broke the CPU or access to the device by a mistake in the browser on it. Now that doesn't mean that you will maybe get access to the secret keys on there, because it might be a different privilege level, but it does show you that it's by far not always the most logical way to go for a side channel attack if there are so many other ways into a device. So it's only when all those other angles are closed that a side channel attack becomes relevant. Okay, on with demos. So, let me think. Measurements. The thing we are now switching to is a smart card. Why? Because it's a very bad smart card, which makes it very easy, well, easy is a big word maybe, which makes it likely that we can do it in a live presentation. Normally you do have to take, a couple of thousand measurements maybe, which takes a couple of minutes to run, and then you need to do your analysis, so it all takes a little bit much time for such a presentation. However, with this card we hope to do it in 500 measurements. So we'll now switch, and Jasper will set up and run the...
Want to get a key in there?
Oh yeah, good point. We actually had the opportunity to put a key in there by choice and see if we can break it. So, does anyone know 8 bytes? Well, he just started typing. DE? C0. Okay, 3 more. 8-3. Oh, I know it's the last session. Okay.
And one more, I think.
And one more?
7F.
Okay.
Gotcha.
Let's go. So now what the tool does, it just, damn, is it yellow?
Yeah, I tried this one already.
This is, I don't know. Ah. Okay. So what the tool does, it just runs, first it programs the key in the card, and then it just runs over sending random data, triggering the measurement, getting the measurement out, and then also getting the random reply, the encrypted reply back, and storing that with the trace. So every measurement has its own input and output data, so that we can then use it for the correlation attack. So, well, this will be measuring for 2 or 3 minutes, so I quickly go back to explain to you this attack.
Suppose in building the smart card you limit the number of times it can be used, so that by the time we do this analysis, the smart card is probably not so good.
Yes. The question is, what if you do just limit the number of acquisitions that you can do, just the number of transactions? That's